easiest detail to find out about a quadratic is the shape. What's the shape of that graph?
Parabola.
Okay, so if we have a quadratic function, we have a parabola. Now, we need to be careful though, because that's a curve, sure, but have we looked at any other curves this semester?
Yes.
Which one?
Exponential curve.
So remember, we looked at exponential curves, didn't we?
Yes.
So is it just because it's a curve, it's a quadratic?
No.
No, right? Hey guys, right here, we need to be careful on the different types of curves. Exponential curve is exponential function. That's not what we have. This quadratic, or this parabola is a quadratic function. Now I want to break down a couple of details here to make sure we keep in mind. What is this point right here called?
Vertex.
Well, the whole thing, so first off, is this concave up or down?
Down.
Concave up like a cup and concave down like a
Frown.
Is that a cup or is that a frown?
That's a frown.
That's a frown. This joker is concave down for sure.
Yes.
But I'm asking, what is this singular point right here?
Vertex.
That's known as my vertex. The vertex is either the maximum when it's concave down, or it is the lowest, what do we call the lowest then? Maximum or minimum, right? So that vertex is either a maximum or minimum, depending on if it's concave up or down. Now, some people notice something, and I need us to pay attention to this detail, okay? Like, right here, there's a line. Whether it's drawn there or not, it's understood. Anyone know what that line is called? It's creating what? Symmetry, right? If we've drawn this perfectly, isn't the left side identical to the right side?
Yes.
So this right here, the line that goes through the vertex is known as a line
No symmetry.
of symmetry. Now I want you to keep that in mind. That line is known as a line of symmetry. Now when I grew up learning these terms, we always called it an axis of symmetry, so you may hear me call it that every now and then, but the more common term today is line of symmetry. Okay, but line or axis of symmetry. Just like you have X and Y axes, right? So line of symmetry, there it is. That's my quadratic, that's my parabola. Questions about this shape? So if you see a parabola, what do you know about that function instantly?
Line of symmetry vertex.
Quadratic.
Well, I know what about the function.
Quadratic line.
How'd you tell? It's hard to learn when you turned around the other way. Thank you, sir.
Quadratic.
So when I see a line or I see a parabola, I got a quadratic function. And that's how I see it graphically. Okay? One thing I do want to point out is we should always try to get back to the x-axis. And if we do, we're going to see it there. How many, did anybody start at like a 0?
No.
But guys, why would it make sense to use a 0?
Good. It ain't nothing.
Let's say if you were doing 0 times something, it would have been 0 regardless.
So, but here's the thing. Does it make sense mathematically, or does it make sense in the real world to have a 0?
No.
No, because you can't have really 0 height or 0 base. However, mathematically, would it make sense to have a 0 in there?
Yeah.
Okay? Because if I put a 0 right here, what does my base have to be? 50. 50 times 0 is? Okay. Down here, I would have a base of 0, height of 50, and this would be 0. By the way, I want you to notice, right around this vertex, what is there in the table even? Well, but what is there? There's an S word.
What?
There's an S word. There's what? Even in a table, there's symmetry there. If I found my vertex, isn't there symmetry around that vertex?
Yes, something like that.
That maximum? Now, this is something that we didn't quite get to, but it's because we didn't draw it out. We didn't write it out. When we had a linear function, how did we know if it was a line in a table? In a table, how did we know if it was a line? Not just repeated addition. There's a C word in there. Constant repeated addition, right? Constant added rate of change. How do we know if it was exponential? Constant multiplicative. So we can't have that. It's not one of those two, but let's look to see if there's actually a pattern. 225 plus 175 is 400. 400 plus what is 525?
125.
125. Anyone know what I need to add to 525 to get to 600?
75.
Just 75. 600 is 625.
25.
625 is 600.
Minus 25.
Now-
25.
I want to point this out. I need you to notice this, right? Is that constant?
It'd be linear function. If you
Mm-mm.
Ooh,
linear
ooh.
function, right?
Hold up. So first off, this is not a function, right? It's a what?
Linear.
But there's an R word to describe this blue section.
Ratio.
Not ratio.
Radical.
Right.
Rate of change.
That is a rate of change, isn't it?
Yes, Lord.
Now, if I were to graph this rate of change, what would I see?
Linear function.
Wouldn't that be linear? How do I know this is going to be linear? You see how it's constant additive?
Yes.
Right? If this is constant additive right here, this is constant additive right there, then this rate of change is what?
Linear.
Linear. Not just linear.
Linear function.
Linear, not function.
Rate of change. Additive. Rate of
Additive
Oh,
rate of
okay.
change. Aren't we adding by those values each time?
Yes,
Yep.
sir.
Yeah.
So what type of rate of change does a quadratic have?
Linear divisible.
Linear,
Rate of change.
not just linear, come on.
Or linear additive.
Linear, additive. Remember, a linear function had a constant additive rate of change. A quadratic function is going to have a
Linear additive.
linear additive rate of change. I need you to go grab a seat. I need you to get out the Frere model that talked about linear versus exponential versus quadratic functions, right? I had all three of them on there. I need you to make some notes to your future forgetful self about quadratics as graphs and quadratics as tables. So update your information to your future forgetful self. Representation, quadratic is a type of what? Function. So what's the one representation we still have not quite addressed?
Give me a minute. You record?
Yes. What representation is this?
Table.
Table. We got a table. What representation is this? Okay, we got a table. We got a graph. What have we not done? Algebra and equation. So remember, y'all kind of made pictures to get us to this point. The big three. Hey guys, listen. CJ. The big three are graphs, tables, equations. Pictures are really good if you're really stuck. They may help you visualize things. A lot of math starts as a verbal representation. But the last real one we have not worked with is algebraic. So we need to look at this. I'm going to kind of step y'all through this a little bit more because I don't need you to create your own algebraic quadratic ones yet. I need us to be able to recognize them. We're going to start getting into how to create them tomorrow. So when I look at this whole context, we were looking at what again? What were we trying to maximize? Find the most of? Area, right? Remember that vertex, by the way, was our maximum, right? This right here, my vertex, where I had that symmetry, was my maximum. But we are trying to calculate area. And how do we calculate area?
A equals B times H.
Okay, b times h, base times
Height.
height. Now, I want to point this out. Every function you have, or every equation you've ever created and graphed had how many independent variables? It only had one. How many independent variables does that area equation have? Say, area right now is depending on both base and...
Height.
So how many independent variables does it have? Two. I need it to only have one. I need it to only have one. So I need to rewrite that expression for base in terms of height or height in terms of base. Any ideas how I could show a relationship between the base and height? There's actually 3 different ways to go about this. Anyone know what kind of relationship there is between base and height?
Oh.
No? See, I see that relationship right here.
Oh. There is
I see the relationship right here.
additive.
But say it again.
Additive.
Is it just additive?
Constant.
Is it? Wait, it's what type of additive?
Constant.
It's constant additive. So it's got a constant additive rate of change. And I look at base and at height. So what type of relationship is it?
Linear.
Say it louder.
Linear.
It's linear, isn't it? How many of us noticed that the base and height were adding or subtracting by the same amount each time? You did? Good.
Yeah.
That's something we should notice right away. That's a linear relationship. We want to recognize that. So if this is linear, all right, I want you to go back to your vertical surfaces, and I want you, and notice I rewrote y as h. I want you to write an expression or an equation here for what the height is. Now, one thing I will note about that height is that my x here is actually going to be what variable? What is the height depending on?
Base.
The base, right? So this x is actually going to be b. I need you to find what goes in those slots and write an equation for what the height is depending on what the base is. Is that clear?
Yeah.
No.
Yeah.
Okay, let me ask this. Who's unclear on this? Okay, let me remind you this. Let's look at this, and I'm going to have you go work on this. What type of relationship do these two variables have? It is linear. Wasn't there a constant additive rate of change?
Yeah.
Okay, so I want you to write the equation of that line. But we're letting y be h for height. We're letting x be b for base. I need you to find m, and I need you to find this b. And notice that's a different type of b than this one. Think about what m and b stand for. Let's get up. Let's try to write that equation. Y'all have to do this for your demonstrate your understanding.
Jenny, I don't have that paper.
You don't have that paper. What paper? Okay, so let's talk about this equation. All right. So, two things. One, I'm glad that a lot of us realize this. Very quickly, a lot of us realized that that y-intercept had to be what? 50. How do we know that that y-intercept was 50?
Because it's the zero.
The zero, right? The input is what?
Zero.
Zero. That input of 0 is telling me my y-intercept is 50. Now, what is this -1 right here? Say it again, Lucas.
Because the rate of change of it is 5. And -5 is 5.
So
5 and -5 divided by 2.
notice this, the notations here, the annotations, they said slope. And remind Lillian, how do we calculate slope? Hey, Jay, put that down so you can focus.
She came with
So remember, you can do rise divided by run, but on this table, the change in y divided by the change in x is best, or change in your output divided by your change in input. And 5 divided by -5 is -1. So there's my slope, there's my y-intercept. Now, two things I want to point out about this. First, if I were to add b to both sides, not that you need to, but if you did, hey, I'm still talking and I hear dice rolling behind me, and I don't want to turn around and see dice and kind of blow up at people because we're not trying to learn something. So let's fix that. So, h equals -b plus 50. If I were to add b to both sides, notice I can do this, because what's -b plus b? -b plus b.
B. Positive B. Positive B.
How about 0?
Here we go.
If it was -5 plus 5, what would I get? -5 plus 5 is? 0. -7 plus 7? 0. So -b plus b is? 0. The reason I'm pointing this out is h plus b then would equal, hey guys, did the height plus the base always add up to 50? Look at that table. The height plus the base was always 50, wasn't it? Okay? So, I want us to recognize these details. They agree with each other, and I just want to see that. But again, if we recognize it's linear, y equals mx plus b. Now, this is the key, right here. To help us understand the quadratics from an algebraic perspective, if h is equal to this, what can I do with that -1b plus 50? Think about this equation. Think about this equation. What can I do with that -1b plus 50? Multiply what?
Wait. No, not multiply. Can you divide?
means I want you to keep thinking. Okay? Let me point this out. This negative 1b plus 50 is equal to h. So what can I do with this equation? Say again. Okay, let me ask you this. If I were to tell you h is equal to 7. Hold on. If I were to tell you,
Substitute.
oh, what was it?
Substitute.
Oh my goodness, it's like we did this earlier this year with the bottle and the cork and Roy and, what was his name? Joel, that's who it was.
What was that?
Roy and Joel, they went to the pool together the same number of times
Y'all
throughout the
remember that?
summer.
Y'all remember
Oh,
that?
the question, yeah!
I don't know.
Right here though, guys, look. H is equal to negative 1b plus 50. And because this is equal to h, what can I do with negative 1b plus 50? Substitute it for what?
H.
This can be substituted in for h. And so now my area comes out to be b times what's going in the place of h? Not just 50.
50.
Negative
1, negative 1, plus 50.
Guys, that's what h is, isn't it? No matter what the base is, the height is negative 1b plus 50. That's an equation here. Now, we need a way to be able to check and make sure that equation is correct, don't we? Okay, so let me pull this up really quickly. Excuse me.
Hell no, boy.
Can someone erase that table for me?
I will. Why you do so much? With your long head, taco head.
Raise all of it.
No, just half of it.
You do too much.
Piece of wood.
With that taco head. Why would you?
Okay. So, what I want y'all to see really quickly.
You just
It don't even take that long.
You know what I'm saying?
He do too much.
Alright. So, I want y'all to see. You leave that. I want y'all to see, I already have a table in here. Put down my laser pointer, AJ.
Follow him.
So, I already have my base and I have my height in here. And what I did to get the area was I did base times height. Do these numbers look familiar?
Yeah.
Okay. So, what I'm going to do, because I know how to use technology, because technology makes my life easy, I'm actually going to graph those points. What's the button lets me do cool crap though?
Menu.
Okay, menu. Where am I going to go if I want to graph something?
Go ahead.
Graph entry/edit. Now, I want to graph a bunch of points that go together. That's known as a scatter plot. And so my independent variable, what was the independent variable again? What was my independent variable?
H.
Base or height. I'm going to go with base. What was my dependent variable? Now I only see 1 point, but remember how when y'all made your graph, Thrasher? The time is, it ain't time to leave school yet. It's time to learn something. That's the time.
Right.
You remember when you made your graph, how you had to go all the way out to 50 in the base, you had to go up to like 700 in the area? Yes, Mr. King?
Yes,
Great, I'm
Mr.
glad you
Yes,
remember that detail. Okay. So,
Oh, go. Shut yourself up.
well, remember, some of
Yeah, I
y'all work on
think
the table,
SOS
some of y'all
teacher.
work on the graph. But like right here, when we did this graph, then we have to go out to 50 in the base and up to 700 in the graph. But I mean, it's the same thing you saw on the table, right? You did the same thing with the table. Okay, so I'm going to go up to 700. All right, can I see those points very clearly now? What shape does that give us?
I put it back over your
Lay,
head.
what shape does that graph give us?
Concave.
There is concavity there, but there's concavity in lots of things. That's not what I'm asking. It gives us what shape? Guys, it's a parabola. That parabola is concave down, but listen, there's a reason why I'm very intentional about this. Watch. This is going to matter later. This is known as a cubic function. Notice through here, what is the cubic function? Concave down. Through here, though, it's concave. So notice we can't just say concave up or down. We got to know it's a parabola. That's the key here. Now, I need y'all to focus because we need to check to see if this equation is right. We need to understand how to determine if the equation is right. So how am I going to graph this equation? You don't know? Yeah, how am I going to graph that equation on the calculator? No, that's the points. That's not the equation.
Why?
I just draw it. But well, partially, but I'm talking about use the calculator and graph this equation and know if this equation is right.
Oh, how you do it?
Yeah, how am I going to graph this equation, guys?
On the calculator.
Thank you, Thrasher. But how am I going to graph it on the calculator?
On the graph.
Oh, the graph.
I'm already on graph.
Type in the equation.
Y'all,
Type in the equation.
hold up. I don't have the equation thing up there. What is the button that lets me do cool crap?
Menu.
Thank you. We got to go to menu.
Scatter plot.
Where am I going to go now?
Oh,
Where am I going now?
three.
What do I want to create? I want to create a
Graph.
graph. Now remember, I have an equation now. If I have the equation, I have a function. And so I'm going to type in, instead of b, I'm going to use x. X times negative 1x plus 50. Now, I want y'all to listen to what Marge just said, because he actually said something very intelligent we need to pay attention to. He said, if I want to graph that, I just need to trace those points. Isn't that what you said? So if this equation is right, what should it do? What should the graph do? It should connect those dots, right? So is that equation correct? Why does it need to connect those dots? This is going to be foundational for what we do tomorrow. And I want y'all to understand, I don't know if you've heard me say this a lot, but have you noticed that I say this is foundational for the next thing we do?
Never heard of it.
Seriously? You better start paying attention because I say it all the time. I would say at least, because guys, well listen, the reason why I do that is, the way that I teach is, I'm still talking. The way that I teach is, I know where we're going, and so I make sure that I hit the building blocks to get there so that you can build on it and have a strong foundation and understand it. Now, why, guys, why did the curve from this equation match these points?
It's quadratic.
So every quadratic will look exactly like this?
No, it can either be concave or
They
curvaceous.
use this,
It's gonna go like that.
But like, how did we know that this equation had to go through those points?
Because of the
Let me ask you this. That table and this graph, do they match? Hey guys, listen. Does that table and this graph match?
Yeah.
But they don't look alike, do they?
No.
No.
So why do they match?
So they numbers.
Say it again, Kyla. What's that mathematical term for they look different but tell the same story? They're equivalent, right? Okay? Hey, shh. Listen. They are what again? Equivalent. What does it mean to be equivalent though? Like, yes, they look different but tell the same story, but what does that mean? Let me ask this question. Let's get over real quick. Listen. It doesn't matter which representation I look at, a height of 5 should map to what? What should the height of 5 map to? 225.
225.
What should the height of 10 map to? 400. 15.
525.
So they're equivalent because no matter the representation, the same input maps to the same outputs. Why are these equivalent? Because it doesn't matter whether it's an equation or whether it's a graph, the same inputs are mapping to the same outputs. So first off, is this equation correct? Is it equivalent to the table and to the graph? Do the same inputs map to the same outputs? That's how I know. Listen, one of the foundational, the foundation pieces of the proficiency scale is literally being able to identify equivalent functions. How do you identify it? If the same inputs map to the same outputs. Now, one thing I want to point out to you about this, or there's two things about this equation, then you're going to do notes and we're going to wrap up the day there. But, first off, what type of expression was this? How do we write that equation? Because this was what? What was this? So it was linear. Didn't we say that the height, depending on the base, was linear? Yes, Mr. Kenny. Great, guys. I'm glad two of us said yes. All right, linear, right? Does anyone know what this is? Just b on its own. What type of function that would be? Like if I were to graph y equals b, what type of function would that be? So if it was exponential, remember I need a variable in the what? In the exponent? Do I have a variable in the exponent? No? Ladies, get a hold of yourself and try to learn something. Focus. Focus. How about if I write it this way? That's just, what's 1 times b? What's 1 times b? B. And b plus 0 is b, right? This is b right here. What type of function would this b be? What type of function would this be? Someone said it.
Line.
Would that be linear? Y equals mx plus b? So this is what? So, I need you to hear me on this. A foundational piece of it. Mr. Kenny, I can't believe you get upset with me because you're trying to teach and I'm ignoring you.
I didn't. You gotta stop sounding like it.
Y'all gotta stop complaining. Oh my gosh. Alright, listen. A quadratic. One of the foundational pieces for a quadratic is that it is a linear expression times a linear expression. That's going to matter later. And that's also why, what's something that we call things that are multiplied? It's a word that we've used. It's a what? Multiplicator. Don't we multiply factors?
Oh my God.
That sound familiar? Right? We multiply factors. You see how I'm multiplying these linear factors? So you know what I'm going to call this form? So this is known as the factored form of a quadratic. So, listen. One way to recognize a quadratic is it's a linear expression times a linear expression. Why you got your backpack on? We got 10 minutes left. And you need to do notes. Oh. But there's something else I need you to do once we're done doing notes.
I stood candy.
Okay, so a quadratic is a linear times a linear. Okay, so one way to see a quadratic is a linear expression times a linear expression. Now, does anyone know anything else I could do with this b to get a different form? Guys, what can I do? What are those arrows showing? What can I do with this base? I could. There's a D word though.
Distribute.
Distribute. Can't I distribute that base right there? Okay? What's B, and I'm just going to write this as a negative B. What's B times a negative B?
B times negative B.
But how many B's do I have? So how do I show that I'm multiplying B twice? See, that's multiplication, which is repeated addition.
Yeah.
I need to show that I'm repeatedly multiplying. What exponent? 2, right? How many B's am I multiplying? 2. So it's negative B squared. B times 50 is 50B. This is known as the standard form of a quadratic. Okay? This is known as a standard form. Hopefully we saw ax squared plus bx plus c last year. For standard form. If not, I'm introducing it. But here's what I need you to see out of this standard form. What is unique Notice that word? What is unique about the standard form of a quadratic that we have not seen in any other equation so far? What is unique in this quadratic that we have not seen before?
That's the equation. Y equals A, whatever that is, that's quadratic.
That's the standard form of a quadratic, yep. Aww. It's a good thing it's like, I don't know, it's in alphabetical order, it's nice and easy, ax squared plus bx plus c. But guys, what does this equation have that none of the other forms have had, none of the other equations have had?
See?
Have we seen anything with a square yet?
No. See now?
Till now. So what makes a quadratic a quadratic? A square. And it's called a degree, the highest power. So the highest power of 2 makes a quadratic. So if you see a highest power of 2, guess what type of function you're dealing with?
Quadratic.
Quadratic. Okay? That's everything with linear, exponential, quadratic. So now we know what a quadratic looks like as a graph. We know how to identify a quadratic in a table, and that's how we identify a quadratic as an equation. Either, at least so far, a linear times a linear, or a highest power of 2 in standard form. Get your notes so that you have everything you need for quadratics. When you are done with that, I need you to cut out the relations on M1-41 to M1-45. You will probably have to get those pages out of the book back there. Yesterday, I think you were supposed to cut out M1- or you're supposed to tear out M1-31 to M1-45. So tear those pages out. After you tear those pages out, then cut out the relations on the pages I have identified.
Don't mess with this camera.
So, get what notes you need to about quadratic equations, but then you need to quickly tear those pages out and cut those relations out.